Okay, so let's actually dive into some of the calculations we're going to make for this real world example. So the first thing we're going to do is we will put all of those scores that we originally saw into a larger spreadsheet. What you can see here is there are actually a number of different calculations that we'll need to make. And so what I've tried to do is to make a column for each one of those. Remember, we had the deviation scores, which were like x minus mean x and y minus mean y. We had the cross product, which is simply going to be x minus mean x times y minus mean y, and that's going to give us the cross product. We had our deviation squareds, and then after that, we're going to use each one of these to calculate out a few final variables that will help us to build our beta zeros and beta ones. So the first thing we're going to do is we need to calculate our means, our averages. So what you can see here is I've already calculated the mean score for exam 1. In other words, remember, we just add up all the scores, divide by 25, the number of students in the class. And let me show you what that would actually look like on our graph of scores. So remember how we said, knowing nothing else, the best guess for a given score is going to be the class average. Well, if I knew nothing about this class, or nothing about a single person except that they were in this class, and I was asked to guess what is their score on exam 1, my best guess would be to simply guess the mean, or the average. So that's how you might imagine this plotted on this graph of scores. Here's the mean. And from this, you can see, and we'll do this in a little bit, that some people score above average, some people score below average, some people score way above average, some people are almost on the mean, and these are each going to be deviations on that x-axis. So next what we need to do is we need to calculate our average final grade. In other words, what did the average student in this class get? Again, 88.2, draw whatever conclusions you want to about me as a professor, but the students, for whatever value they got in their class, they were at least happy at the end of that first grade. So the average score is 88.2. If we're going to plot that here on the very same XY axis, what we'll see is it goes right here. We saw this line a little earlier. Now I want you to notice something in particular. Notice where these two lines intersect. The mean of x and the mean of y should always intersect on this regression line. In other words, for someone who scores exactly average on test 1, the best guess for that person is going to be that they score average on their final grade. And the line of best fit is then going to tell us whether someone who scores above average is going to be best estimated by an above average final score. But we'll get to that in just a second. What I want you to notice right now is that the two means tend to cross right on that regression line. So what's the next thing that we'll have to calculate? The next thing we're going to calculate is this deviation score right here, the x minus the mean of x. So remember here for this person number 1, we have their, we don't have their y score, we have their x score. Pretend I didn't do that. There we go. We have their x score. And we have the mean of x down here. So in order to find their deviation score, what we do is we take 50 minus 46.44, and this is what it's going to look like. We take their score right here, 50 minus 46.44, and what we're going to find is that they have scored above average. So this is what that deviation score would look like. This person gets a deviation score of 3.56. We're going to do the same thing for every other person in the data set. So now we have deviation scores for everyone. Now the next thing we need to do is to calculate out the deviation score for the y-axis. So for this first person, I want to know, is their final grade above or below the average final grade of the class? So I'm simply going to take 90 minus 88.2. So again, let me show you what that looks like on the graph. We have 90 minus the average of 88.2. And again, this person has a positive deviation score. In other words, they were above average in their final grade as well, just as they were above average on their exam 1 score. So here we have a positive 1.82. And I'm going to do the same thing for the rest of the people. So every person has a deviation score on X and Y. Sometimes they're both positive and positive. Sometimes here's someone who scored a little bit below average on their first exam, but scored a little bit above average on their final grade. Sometimes you have the reverse, above average on that first exam and below average on the second exam. And sometimes you get people who scored below average on the first exam and below average on their final grade. In the end, what we're going to need to do is to take both of these scores and multiply them to get the cross product. Remember, what this is going to tell us is where, in general, these points are located. Are they in which quadrants are they located? So let me show you what that looks like. Remember, right here is one cross product. So this is one in which they have a better than average exam 1 score and a better than average final grade. So this person's cross product is going to be positive. Down here, we have someone who has a lower than average exam 1 score and a lower than average final grade. But remember, when we multiply a negative times a negative, we end up getting a positive. So this person's cross product is going to be positive. In other words, up here in this quadrant, we tend to have positive cross products. Down here in this quadrant, we have positive cross products. And it should come then as no surprise that a line that goes through these two quadrants is going to have a slope that's positive. In other words, a positive correlation or relationship between two variables. However, down here, sometimes we have someone who scores above average on the first exam and below average on their final grade. When you multiply this, a positive times a negative, you end up getting a negative cross product. And similarly up here, someone who scores below average on their first exam and above average on their final exam, you take a negative times a positive, you're going to get a negative. So up here and down here, we get negative cross products. In other words, what points in these two places are going to tell us is the higher someone scores on their final grade, the higher they're going to, or the lower they're going to score on that exam 1. Or another way of saying that, probably the more accurate way of saying it is, the lower they score on exam 1, the higher they're going to score on their final grade. Or another way, down over here, the higher they score on exam 1, the lower they'll score on their final. In other words, more points down here and up here indicate that there's a negative relationship between variables. So you can start to see how, although I've scribbled all over this, how the accumulation of dots, either in an upward direction or downward direction, is going to lead to a positive or negative slope. So we've done the cross product for one of those dots, one of those data points, and we're going to do it for everyone else. So what you'll start to notice is sometimes you have positive cross products, sometimes you have negative. Sometimes you have big positive cross products. This one is going to add a lot to the slope of the line. Sometimes you have bigger negative cross products. This one is going to take away from the positive slope of the line. So in general, the more of these big positive cross products we have, and the fewer of these large negative cross products we have, the more positive the slope is going to be. In the end, what we're going to need to do is to take, in just a minute, we're going to do the sum of all those, kind of add them up together. And when we add them up together, what we'll see is that the positives and the negatives tend to balance each other out. So the next thing we're going to do is to calculate the x minus the mean x squared. In other words, the deviation squared, which is pretty straightforward. We just take 3.56, square it to get this, and do that for every other one. negative 1.44, when you square it, is positive 2.0736. So remember, everything here is going to be positive because it's squared. This is, in general, telling us how much deviation or how much variability there is in these data. And we're going to do the same thing for y. This, and the x minus the mean x squared, is going to tell us how much variability there was on test 1. And this is going to tell us how much variability there was in the final grade. So here we take each one of these deviation scores in y, we square it, and we get the squared deviation score. So then the next step we're going to do is to sum up all of these down below. So we're going to have the sum of the cross products, the sum of the squares x, and the sum of the squares y. And then we're going to move into the final phase where we'll use each one of these sum scores and covariance to calculate out some of the final elements we'll need to calculate our line. So up here, we take the sum of all of our cross products divided by the number of observations. So here, we're going to get that from down here, 107.2, divided by the number of observations, which is 25. So 107.52, or sorry, 107.20 divided by 25 is going to give us 4.29. This is the covariance of x and y. Next, we're going to take the sum of squares x. And that's simply this number right down here. We've squared all of our x deviation scores, and we just simply move that number up here. We're going to do the same thing for our sum of squares y. That's just this sum of squares, sum of all of the deviations along the y-axis. In other words, this gives us kind of a rough measure of how much people are varying in their final grade. But if we had 1,000 of these observations, this number would be much, much bigger. So we want to know in general, what's the average deviation around the x and the y? And so that's where we get the variance. So for the variance, we're going to take the sum of square x right here, and we're going to divide it by the number of people, number of observations we have. So if we take 281.31 divided by 25, it's going to give us 11.09. We're going to do the same thing again for the variance in y. We take the sum of squares y, which is that, divided by 25, and that will give us 11.25. Back here, this one, the variance in x, should have been the sum of squares x, not the sum of squares y. So 266.16 divided by 25 is going to give us 11.09. My apologies. Okay, and now we're just about ready to calculate out our beta-1 or our slope. So we have all of these different elements, our covariance, our sum of squares, our variance in x and variance in y. And to calculate out our beta-1, what we need to do is to divide the covariance of x and y, that's this number up here, and divide that by the variance in x. So take a second just to think about what we're doing. The covariance of x and y, this is, on average, are people scoring positive in their cross products? Meaning, are they in that upper right or the bottom left-hand quadrant? And if so, how much? How much is the average covariance? If it's really big, then we're likely to have a strong positive relationship. If it's very small and positive, it's likely to be a small positive relationship. And so for the beta-1, what we want to know is what exactly is the slope? How much are people scoring in those quadrants based on the average amount that someone differs in their exam 1 score? And so what we do is we take this covariance of x and y, we divide it by the variance in x, and what we end up getting is 0.4. What 0.4 is going to be is that's going to be the slope of the line that we get in the end. And I'll illustrate this for you in just a second. Finally, for beta-0, remember this is the y-intercept, and beta-1 is the slope. For the y-intercept, all we're going to do is we will take the mean of y, that's over here, right here, 88.2, minus beta-1x, minus beta-1, which is here, times the mean of x, which is 46.44. And that's going to give us 69.51. Now, leaping from each one of these individual variables to this very last set of variables, the beta-1 and beta-0, might have felt like a bit of a leap. I'm going to show you in just a minute on the last video what that looks like visually.